So we have learned Lenzs law in the previous video, and try to get an idea of how it is that the direction of induced EMF can be identified using Lenzs law. We tried an example, but we are going to definitely need more examples in order to completely understand Lenzs law. So let's make an attempt in that direction. All right, so a quick reminder what the Lenzs law was actually. So Lenzs law, which was originated from the law of conservation of energy, basically says something like this, that the induced EMF in the coil, and actually EMF is induced due to changing magnetic flux. We already know that from Faraday's law. Anyway, Lenzs law, read with me please. The induced EMF is in such a direction that it tries to oppose the changing magnetic flux. Actually, I should write a little more here, which created it. And don't worry, I'll read it again. Which created it. And actually, it's like if this were one of those English language questions in your grammar section, what does it indicate in this statement? First answer that question. Let's focus on that. The induced EMF is in such a direction that it tries to oppose the changing magnetic flux which created it. Let's make this English class for a bit. Yeah, what does it refer to here? Option A, I don't know, induced EMF. Option B, direction. Option C, the induced EMF. I think I said that already. Option D, flux. Anyway, the answer is the it here refers to induced EMF. Alright, so wherever you see it actually means induced EMF. Alright, now let's look at the sentence once again. I'm trying to go very slow here. In fact, I'm being very careful with this video because if you learn to find out the direction of induced EMF, half the job in electromagnetic induction is done. Literally half the job is done. So this video is going to be very important in that way, right? So let's try to learn this. So EMF induced will be trying to oppose its own creator, So changing magnetic flux creates the EMF, but the EMF is opposing that changing magnetic flux. Or to sum it up for the nth time now, that if the magnetic flux which is creating EMF is increasing, then the EMF induced will try to oppose that. That means if the flux is increasing, the induced EMF will try to decrease it, and if the flux is decreasing, the induced EMF will try to increase it. Is basically what the Lenzs law is all about. Alright, fine. The statement seems pretty simple. If why is he making such a big deal out of it, right? Let's see. With the next few examples, it should be very clear. Alright, so one of the examples I took in the previous case was this. Something like this. Let's say you have a conducting loop which has no current in it right now. We have a rod whose north pole is facing the ring and it is given some velocity v. Once the magnetic field comes in the vicinity of the conducting ring, this ring, again I'm saying, does not have current in it to begin with. The changing magnetic flux is going to induce EMF, and therefore this ring is going to get current. Alright, and of course we have Lenzs law to support this. And if there is any doubt with this, you will have to watch the previous video. But yeah, the point I'm trying to make here is we have already discussed this case. Let's say these are the field lines. At least I'm concerned about north pole alone, at least at this stage, because that's the one which is facing the ring, right? So with these magnetic field lines, the velocity is in the direction of the ring. If this is the case, then the induced current in the rod will be in this direction. The current induced will be in this direction. That is, the current is coming out at the topmost point and the current is going in at the bottommost point. So you can imagine the ring, actually this ring, the red color ring, is perpendicular to your screen. Okay, and to give you a better idea, I'll just try to draw. Just give me a second. I think you'll get a better idea with this. The bar magnet is actually moving along x-axis. The bar magnet is actually moving along x-axis, and the ring itself lies on YZ plane. This is Y and this is Z axis. So I hope with this you get a better idea, right? I don't know, this is the negative Z axis going inside the plane. This is the negative Y axis going below, and this is negative X axis. So you get the idea, right? So ring lies on the YZ plane. So over here the current is actually coming out of the plane, and over here the current is going inside the plane, and that's Lenz's law for you. Lenz's law actually indicates this direction of induced current. And how do we know that this is going to be the direction of induced current? To make it more clear, I'll current is like this, in this direction, like that and like that. I hope you get a better idea with this. Alright, so that's the direction of, I think I messed it up, right? So yeah, that's the direction of induced current. Alright, so how do we decide this? For this case at least, you're going to have to watch the previous video. I'll be giving more examples like this in the current video, but this case is already, it has already been discussed in the previous, in the very previous the video before this video, that I've already discussed that. Now for the real deal, right? Let me take more examples like this, and now is the time for maximum attention. Let's say I have a ring like this. I have a ring like this, sort of attached to a wall over here. So we have a ring attached to walls on either sides. So actually it's a horizontal ring. Okay, this is a horizontal ring attached to these are the walls. It is attached to the wall, and we have over here a bar magnet which is something like this, with the north pole of the bar magnet facing the ring. South pole of the bar magnet is of course away from the ring, and this ring, actually I'll try to create a better image of the ring. So try to, this end of the ring is actually outside the screen, and the ring actually is perpendicular to the screen again. So this end of the ring is outside the screen. So I'll try to make it thicker so that you'll get an idea that that part of the ring is outside the plane of the sheet. Alright, so that's the situation. And you also have over here, now with this situation, with the ring being horizontal, let's say you're trying to watch the whole situation from below. From below you're trying to, let's say this is your eye, you're seeing the whole thing from the bottom, right? If we drop this bar magnet now, we're dropping this bar magnet with this orientation. If we drop the bar magnet, the question is, if you're seeing from here, will you see the current in the ring in clockwise direction? Will you see it in clockwise direction, or will you see the current in anti-clockwise direction? That's the question. Alright, so If you have already understood Lenz's law, you should be able to answer this. You can just pause it and just answer that, right? Yeah, let's see. So this is the situation, right? Now the 4 crucial steps that you are going to follow in order to use Lenz's law, and I can't emphasize enough the importance of these 4 steps. In fact, the third and fourth are most important. First 2 you can easily do it. So first step is, and I'll write it also, what does this mean? First step is identifying the direction of original magnetic field. Identifying the direction of original magnetic field. BO stands for original magnetic field. I'll just write it here. So wherever you see BO is actually the direction of origin. BO is basically original magnetic field. What do you mean original magnetic field? The field which is causing the induced EMF. Alright. Second in this step that you should be doing, second step in order to identify the direction of induced current, is to find whether the magnetic flux, whether it is increasing, whether the magnetic flux which is coming as a result of original magnetic field, whether the flux is increasing or it is decreasing. Identifying that is the second step, which will be again be very simple, decreasing. These first 2 steps are, they are very simple. Third actually is also simple, but yeah, this is where the actual Lenz's law kicks in. Third one is to identify the direction of BI. Third one is to identify the direction of BI. And what is BI? BI is the induced magnetic field. Alright, so BI is induced magnetic field. I'll tell you what this whole thing means. Just wait for it. Alright, so BI is the induced magnetic field. Identifying the direction of induced magnetic field. And once you do that, final step is to identify the direction of current. And it's like once you get the direction of current, it's as good as getting the direction of EMF. So you have successfully used Lenz's law once you reach step 4. Alright. And if we do a few examples, the identifying the direction of current is not going to every time make you think that let's go through step 1, 2, 3, 4. No, it will become a second nature to you. But for that we have to understand these initial examples at least very, very carefully. Let's do this. Alright, so first is to identify the direction of original magnetic field. Alright, that seems fairly simple. Look at these white arrows that you're seeing. That is the direction of the original magnetic field which is going to induce current, right? So I think first part is done. The direction of BO, wait, I'll use different color for that. So I think the first step is almost done in no time. BO is clearly directed downwards, right? In this case, at least I can say that BO is directed downwards. Look at this. Look at these white arrows. That's the direction of magnetic field. Alright, so BO, identifying the direction of BO is done. Second is to identify if the flux is increasing or decreasing. Now let's see that. Alright, so I'm thinking, and before that I need to know what flux actually, in what all ways the flux can change. Flux definition is B into delta S into cos theta. This is just a side note for the main discussion. So flux is B into delta S into cos theta. Let's see in this case, is delta S changing? I don't think so. Delta S is the area of the loop in this case, right? So delta S is not changing. Is cos theta changing? No, because theta is not changing. The bar magnet is falling the way it is falling. So as the time passes, theta does not change. So theta is not changing. So but you need changing flux, right? And actually in this case the B which is changing. How do I know that B is changing? Because the bar magnet is falling down towards the ring, at least in this situation. Later it's going to go away from the ring once it is below, but I'm not at that situation. Right now I'm talking about this situation where the bar magnet is falling towards the ring. At least in this case, I'm thinking the bar magnet is approaching the ring. That means the distance is decreasing. And you know that magnetic field is inversely proportional to the square of distance, right? So as the distance decreases, the magnetic field increases. So I think the second part also we have kind of answered, the second step in order to identify the direction of induced current also is done in this case. And clearly in this case flux is increasing. All right, flux is increasing. And now that we have identified this, let's go back to Lenz's law a little bit. You have identified two things. One, the induced magnetic field is downwards. The original magnetic field is downwards and the flux is increasing. Okay. But according to Lenz's law, the induced current should be such that it tries to oppose such any change of flux, right? So here the flux is increasing, meaning the flux due to induced EMF should try to oppose this. That means it should try to decrease this flux, and it can do that if and only if it gives the induced current gives a magnetic field in this direction. That means this is going to be the direction of induced magnetic field. Now the third step, very important, let's focus on this once again. All right, so I'm going to repeat these three steps once again. Original magnetic field downwards, very clear. Flux is increasing because of this reason. Flux is definitely increasing. Now that you have decided that, according to Lenz's law, if flux is increasing, the induced current will try to reduce it, and if the flux is decreasing, the induced flux will try to increase it. Induced current, will try to increase it, right? So here clearly the flux is increasing. Since the flux is increasing, the induced field should try to oppose that flux. Only then can it oppose the increment of flux, right? So induced magnetic field has to be in upward direction. This is the direction of magnetic field which the induced current is going to give, right? Now for the final step, right? What is the direction of current? Now to answer that, you only have to answer this part, that what can be the direction of current? What should be the direction of current in the ring? What should be the direction of current in the ring that can give magnetic field in upward direction? Again, for the nth time, BI, the induced magnetic field, is that magnetic field which is coming as a result of the induced current, right? And that induced current is that of the ring. All right, so for this we can go a little bit behind in our discussion and remind you this, that if you have a ring like this in which the current happens to be in this direction, let's say the current happens to be in this direction, how do you identify the direction of magnetic field in such case? It's the right hand rule. Use your right hand to hold the ring itself. So if you hold the ring itself with your right hand and bring the thumb out, right hand, such that your fingers are in the direction of the current, right? And if you bring the thumb out, that is going to give you the direction of magnetic field, right? So in this case magnetic field is in this direction, and that itself is actually, in this case right here, in my present ring case, is the induced magnetic field. So clearly the current has to be, according to that right hand rule, the current has to be in this direction in order for us to get the induced magnetic field upwards, right? Why do we need induced magnetic field to be upwards? Induced magnetic field, if upwards, only can oppose the increasing flux, right? So this is all according to Lenz's law, whatever discussion I'm making. And wait, now that we have decided the current is going to be in this direction, if you're seeing from below the ring, to you this current is going to appear anti-clockwise. All right, I hope you understood this. I'll be taking more examples in the next videos. All right, thank you.